And welcome to another Creature tutorial. In this tutorial, we're going to talk about physics motors and how they affect your animation. To start off, let's answer the question, why would you ever want to use a physics motor? Let's say you want to animate a floppy tail or a piece of garment that swings about and reacts to the character's impulses and underlying actions. Or you wanted to model flesh, how flesh stretches and bounces and is very elastic and how it responds to the skeleton of the character. Or if you wanted to model muscle activation, any kind of dynamic effect is a very good candidate for a physics motor. So that seems like a lot to cover, so let's just jump in. Let's start installing a physics motor on these set of bones. I have a dragon head with a neck over here. So if I select the bones over here, and I click Install Motor, and I click Bend Physics Motor. Now let's play the animation, see what happens. Oh, look at that. Basically, the neck is bending, and it looks like it's getting influenced by gravity, and there's a slight bounce. So already you can see how it's useful for tail animation, right? You could imagine this is a tail, or in this case a neck. If you have the underlying animation driving this bone, everything else is going to respond in a floppy fashion. So you have your floppy tail or floppy neck. Now, if you click on one of the bones of the physics motor, it says Bend Physics Motor. That means it's of the Bend Physics Motor type. And you have these parameters over here. Let's go through some of these to see what it actually does. First off, you need to understand what stiffness is. And I should actually demonstrate to you what it does so you get a better idea of what it does. So let's set the value to a low value like 5. Stiffness of 5. And if we play it back, oh, look at that. The neck falls all the way down. It's getting pulled all the way down by gravity. And that's because it's a very loose material. 5 is a low value. What stiffness actually does is it tries to preserve the angles between these bones, these chain of bones. So if you have a very low value, that means that it will have a very weak force that tries to preserve these angles. And hence, because it's weak, it's very loose, and so it falls all the way down under gravity. If I set it back to, say, 100, and I play it, you see how it tries to preserve this shape. Cool. So that's basically what the stiffness value does. Now, already you can see how useful it is for different kinds of floppy material. But I'll give you another tip. Let's do something interesting. Let's set this value to 5. Okay? So in the spreadsheet, I have this at 5, and then I'm going to hold this value for, say, 15 frames. So I'm going to set that to 5 as well. And then I'm going to ramp up the value at frame 18 to, say, 100. So what's going to happen? Let's look at the spline to see what's going on. I'm holding this value for a low value, for 5, and then I ramp it up to 100. Okay. So it's going to be very loose. It's going to fall all the way down. And then it's going to stiffen up. Well, let's see what happens. Oh, look at that. It was loose, stiff. Loose, stiff. Right. That makes perfect sense, right? And you can see this is actually very cool because you can use this for some kind of muscle activation effect. What do I mean by that? Well, your muscle is very loose, so it's not tense, so it falls, and then you tense it up, right? So you get that follow-through reactionary effect. So just by keying these parameters like stiffness, you can get some very, very intriguing dynamic effects. So you should use that to your advantage. So that's basically stiffness. Okay, so let's clear these keys now. Let's get back to the original. Say 50. Play back. Right, so there's that bounce. Okay. Now what's damping? Damping is basically how quickly energy bleeds from the system. And what do I mean by that? Well, if I set damping to, say, 100 right now, and I play it, I'll see it's bleeding so much energy you'll see the effect. Well, let's try 50. See what happens. Look at how slowly it falls. It's almost like it's going through ether or some kind of very, very thick material. That's because it's bleeding so much energy from the system. There's so much resistance. You know, it's slow. It falls very slowly. So if I set it to 5 and I play it, Notice very little energy is getting bled from the system. So when I play it, it wobbles a lot. That's basically what, right, that's what damping does. And if I wanted to wobble less, I can up it to 10. Play it, see how it wobbles less. So again, by tweaking the damping parameter, you can determine how quickly energy bleeds from the system. And that again enables you to model different kinds of material. If you're modeling very heavy material, you probably want very high damping. And if you're modeling some kind of a bouncy material, you probably want low damping. So that's basically what you need to do. Okay, if you noticed, we were always in this physics mode called stability. And what is that? Stability is the mode we suggest beginners start with. When you first start tweaking physics motors, stability is a good mode to start with because the system's going to try to make your simulations very stable. Although it might be a little boring. You might not get enough motion or the desired motion that you want. So the alternative is motion. Now this mode is a bit more advanced. It's a bit slightly more difficult to tweak to get the desired results, but you can get much more dynamic behavior. So let's start playing this and see what happens. You see that? So just by playing the motion thing, you get a lot more motion. More interesting stuff is happening already. But it's also a bit more unstable, as you noticed. So typically in motion mode, I require more damping. Because, right, if I have too little damping, like let's say 1, what happens? Look at this. The system's going crazy. It's going haywire. Why is this? Well, this is what we call an unstable simulation. This is what happens when too much energy has been injected into the system. And this type of bad behavior manifests itself when your damping value isn't high enough. So the cure for that is obviously more damping. If I have that to 5 and I play it, right, it's still going a bit crazy, but you see it finally settles down. So you probably need a bit more damping. Say like 15, I play it, right, it's a bit more predictable, as you've seen. All right, so that's damping, and that's the motion mode. Now, what happens? What's the stretch stiffness thing? Well, what happens if I set the stiffness to a lower value? Will something crazy happen? Let's try playing that. Oh, look, it's falling too slowly to see any kind of effect. So let's up the gravity to see what I'm talking about. Let's set it to 0.5. Play. Oh, look at that. The neck just stretched. That's a bit crazy, isn't it? Why is that? Well, I didn't describe to you stretch stiffness previously because that parameter is not active in the stability mode. But in motion mode, this parameter actually has an effect and has meaning. So if we play the animation again, you noticed that the neck has stretched all the way to the bottom, right? Now, if I up the stretch stiffness, say to 200, let's see what happens. You notice it kept the length? So stretch stiffness is like stiffness, except stiffness tries to preserve the angles between this chain. Now stretch stiffness tries to preserve the length between this chain. So it allows you to obviously determine how stretchy the material is. If your material is very, very stretchy, if you wanted to stretch a lot under gravity, you're going to give it low stretch stiffness, very low stretch stiffness. Something like this, which is a bit ridiculous, but you get the idea. It could be for garments, any kind of stretchy material. If your material is not that stretchy, you up the stretch stiffness. In this case, it's still stretchy. And if you don't want it to stretch too much, you have to give it high stretch stiffness. Right. Of course, take note that the higher you set your stiffness values, you should always accompany that by increasing the damping. Otherwise, you might get too much energy in the system and it might go haywire. So remember that. Also, tweaking damping in tandem with stiffness is very important when you're in motion mode because it's just a bit more touchy. But you get more interesting and dynamic effects. Plus, you get to tweak stretch stiffness, which you didn't have the ability to do in the previous stability mode. So previously we saw how to use the bend physics motor, and let's move on. Let's move on to something else equally interesting. So bend physics motors operate on a chain of bones, right? That's what we just talked about. What if we wanted a physics motor that operated on the mesh, the region mesh itself? In other words, we want some kind of physics to affect this area, this region. That's essentially soft body dynamics. That's what we're asking for, and we have that ability in Creature. So how do we do this? Well, before we begin, let's set up our situation or scenario that applies for this case. So let's select these bones and let us put in some kind of simple, say, smooth IK rotate motor, for example. Let's just make it rotate about this point. You know, nothing interesting, just typical smooth IK rotate action. But you'll see in a moment why we're doing this. Okay, so this is all it does. Right. Okay, so now we're going to make this next section over here respond to that driving action of the smooth IK rotate motor, but we're not going to use the band physics motor. We're going to use something else. So now click on the regions tab, and now select the neck region. Right. Now click install motor. Scroll down and you'll see physics motor. It says deform the mesh using soft body physics. So click on that. All right. What's going to happen? Well, let's play it. Well, something unexpected might happen. You'll see. Oh, that is very strange. What's going on here? The mesh just fell all the way down to the ground. That's not very helpful, is it? No, it isn't. So before we have to make this thing useful, we have to tweak it, obviously, and we're missing a very important part. So why don't we select this region again, and this time click Edit Motor. Okay, now we're in Edit Motor mode. What exactly happened just now? Well, what happened just now was that we had a completely unconstrained soft body mesh. So what I mean is no part of the mesh, no points in the mesh were actually constrained to the animation. So it's fully unconstrained, which meant it will obviously fall under gravity because nothing was getting held up. So the solution is to start painting in regions. So like what I'm doing right now, I'm trying to paint like an interior region to make it follow the animation. You'll see in a moment what I mean by that. So these regions in white are going to follow the animation. Think of it as like the interior bone or the core that is going to be driven by animation. And everything else beside it is going to follow through in a soft body dynamics fashion. So if we click Finish Editing, and if we play it, you see that? There's a slight wobbly motion going on while it responds to the driving motion of our smooth IK motor. So we basically have a 2D soft body dynamic solution going on here. Okay, so that is kind of interesting. Now, there are lots of parameters to tweak in this motor. Let's go back to Edit Motor. There's this thing called flexibility. What's that? Well, it does exactly what its name suggests. If I increase the flexibility and play it again, you notice this motion here has a lot more degrees of freedom. It's a lot more wobbly, but it's not just more wobbly. It actually deforms in a slightly more interesting way. There's more avenues of deformation, right, as opposed to the previous one. So if you have low flexibility, your mesh is, as it suggests, not as flexible. It's a more rigid material. I hesitate to use the term stiff. It's more like rigid material. Whereas if you have a more flexible, higher flexibility value, it's going to be a more bendable material, like here. And so you can see how this is useful for simulating or animating any kind of fleshy motion. If you wanted to make this what we have here, like this kind of flesh material, we would use a physics motor on this mesh. So I mean, we can illustrate that. Right? Let's increase the amount of rotation, so you get more reaction. Look at that. So this soft body fleshy type motion is a very reactionary, very interesting dynamic motion that's very hard to animate manually. If you wanted to do it by manually pulling points, you'll take a long time. Trust me on that. But by just using the physics motor on this mesh region, we have easily done it with a couple of clicks. Okay, now if we go back again, just like in the previous band physics motor example, you have a bunch of parameters you can tweak, and they mean exactly what they mean. So you can always lower the stiffness. If you lower to 500, the material becomes very loose. And right, you see how really floppy it is. Now, too low of a stiffness, however, you're going to get a bit too much distortion. So use it with a bit of caution. But just by tweaking the stiffness, you're going to get different kinds of material properties that will suit your needs based on what you're trying to animate or simulate. Very useful for simulating any kind of area or maybe volumetric body type effects. So there'll be flesh, a bit of muscle action, or any kind of requirements that tends towards the soft body physics form. So that's basically the physics motor. Okay, finally, we're going to talk about the pin rope physics motor. And the best way for me to describe this motor is to try out. So let's select these bones. Let's select these chain of bones all along the neck. Click on Install Motor and click on Pin Rope Motor. Right. Let's up the gravity. Let's up it to 0.05. Let's play it. Oh, look at that. So it looks like the neck has formed some kind of suspension bridge with the base and the end getting kept in place, and this thing just arcs down. Now, what is it actually doing? If we click on one of the bones with the motor, you'll notice this handle comes over here. And we can animate this handle. Let's try animating it for a couple of frames. Let's at frame 20 we bring up. Let's see what happens. Oh, so you notice that the end handle is following the intended, or rather the end bone is following the intended end handle. And the set of bones in the middle are basically falling under gravity, responding to some kind of rope physics type action, and yet getting pulled or directed or pinned, that's why it's called the pin rope physics motor, according to the end bone. So we do this, and then if we come here and we move this down again, let's play it back. Right, you can already see how useful this could be. Right, you can use it to animate some kind of neck physics action, and all the bones in the middle will then respond accordingly. You don't have to pose the bones in the middle. You just snap on a pin rope physics motor and then animate the end where you want to direct it, and everything else will fall into place based on physics. Now, of course, all the standard parameters are in as well: stiffness, stretch stiffness, and the like, which I've already described in the previous examples. But what this allows you to do is to direct your physics action. So it's a very useful motor if you want to animate the necks of creatures, or any kind of directable physics action that happens along a chain, and you need the final bone to move or be set in a specific location, and you just want the rest of the bones to follow in a natural but dynamic way. This is when you want to use a pin rope physics motor. So, well, that basically ends the tutorial on physics for Creature. I hope it was very informative for you, and happy animating!